So in the previous video I just copied this code. It's I want to estimate the yield to maturity on a bond, and there is some code here for estimating the present value of a bond using a loop. Then there's a bisection algorithm introduced to estimate the value of the discount rate within a particular tolerance level. And then I have initial parameter values that I've introduced. So that code, if you like, has been copied, and I've opened up the Xcode IDE. I've created a new project. I've got as far as introducing source code. So let's remove this segment of code here and paste in. Okay, and let's see if there's any issues. So I'll just slightly re-edit, and I think there's no initial issues that would appear. Okay, so here we have estimating the present value of the coupons, then the face value, the bisection technique, and then we have some parameter values that we've entered in. So these are slightly different. Face of 1000, coupon rate 6%, market price of the bond here is 1,010.99, 3 years to maturity. M is equal to coupon payments being paid twice a year, so biannual coupons. An initial guess for the lower rate of interest as being almost equal to 0, and then the higher rate of interest, higher initial guess, is 10 or 1000%. 1 here would denote 100%, so very wide range. And then output the YTM. So let's just debug this and execute the code, and the build has succeeded. And then we're just looking to see what output, and we get a value close to 5.6%. Okay, we can check that in a moment. Now, initially I had said this was what we're actually trying to estimate. So really we're looking for a coupon rate, again 6%, but a time period of 3 and m equal to 2, and the market value in this instance is actually 1,010.77. So I'm going to just change a little bit here the values that I have. So this market value 1,010.77, and then we're saying frequency of coupon is actually once a year, not twice a year. And I'm going to go with that lower A and higher B. So I'm going to retain those values. 3 years for the maturity, $1,000 face, 6% coupon rate. With these values I want to discover the yield to maturity, so let's run that again and see what output we get. And again, there shouldn't be any issues with build succeeding. So build is fine, and this instance we get 0.0560006, so very close. Okay, so we can see perhaps if we changed a little bit here the rounding, we might get more precise figures. So 777696. Let's try that, 7696, and okay, so 1,010.7696. 7 0.696. Let's try that. Again, we're getting 0.056008. Looks plausible. And again, if I go back to the original parameter inputs just to compare, now here it's a coupon structure that was used, but this, I'm going to use these parameter values and try to deduce this, if you like, discount rate or yield to maturity. So if we took a face value of 1000, coupon rate of 6, time period of 3 years, frequency of coupon twice a year, if we set this out and apply the discount rate of 5.6%, present value of the bond is 1010. Now in our code we don't use a present value of annuity structure, we're just using this annuity structure to work out the value of the bond. We know the value of the bond, we want to deduce the discount rate, that should be 5.6%. So what if we put in the other parameters? Can we verify 5.6%? Okay, so 1010.91 and 2 equal to 2. Okay, so we go back into our Xcode and again 1010.91 for the market value or the target, and we're changing the frequency of the coupon payment to twice a year. And just to note, this code is not set up using an annuity, it's a loop discounting the coupons. Okay, so let's just execute that and see how it goes. So, and we should get 5.6%. Okay, to know that our code really works, if we set the value, so this is another experiment, if we set the value here of the market value of the bond to be 1000 and the face value of the bond is 1000, and we change this to coupon payment once a year, this has got to be a par bond, and by definition with a par bond, when the face value of the bond is equal to its market price, then the coupon rate should be equal to the discount rate. So the yield to maturity must be equal to 6% here by definition, and that's a good test case. So let's execute again. We should get 6%, and we get exactly 6% as our. So we know this code then is viable and it's working. I initially, just to mention, I initially took this bisection from Volupta. Might have a look at that. And I took it from Volupta. So when I was estimating the value of implied volatility, so Volupta Fabrice Roy has implied volatility code to C++ code to estimate implied volatility. He introduced the bisection technique. So I used this code here, but I do have to make some slight changes. But the basic structure of the bisection technique developed here is where I obtained the bisection C++ code, but I had to switch the location of A and B in the code, and you can verify that by going through it yourself. But that also is an interesting source here for just looking at how bisection can be applied in a variety of different instances. Okay, so going back into Xcode again, we can see that the code works, it's viable, and it produces the correct value using this test case here. Again, if we change this to 2, we should get the same value again of 6%, won't make any difference. And the code looks robust and is viable. Okay, so we get a yield to maturity again of 6%, so the code works.